this cis alkene directly from this alkyne. Now we're starting to look closer to what we're allowed to start with. Now we can actually recognize the new carbon-carbon bonds. These were new carbon-carbon bonds. Well, let me keep working backwards. There's an alkyl halide. You can take a terminal alkyne, deprotonate it, use that as the nucleophile in an SN2 reaction with a methyl or primary, occasionally secondary alkyl halide. Got a carbon-carbon bond forming reaction. So this is something we're allowed to use. This isn't, but that's okay. All we got to do is take acetylene, deprotonate that, react it in an SN2 reaction with ethyl bromide. Now we're back to substances that we are allowed to use as starting material. Then it's just a matter of putting it all together. That was our analysis of the problem. Now we've actually got to write the synthesis. So what do we need to do to get from this to, let me write it this way, what reaction conditions will allow us to alkylate a terminal alkyne? What's the base that we typically use to deprotonate a terminal alkyne? Did I hear somebody say NaOH? That's not. What's the base that we use? Na, not NH3. It's NaNH2. It's the conjugate base of ammonia. So typically we do that in ammonia as the solvent. And then after we deprotonate, we dump in our alkyl bromide. So this is one of those two-stage processes. First you deprotonate the alkyne, then in a separate step you add in the alkyl bromide. And that gets us our first new carbon-carbon bond. Then we got to repeat. You can't pull off both of the protons. It's not reasonable to do that. So you make first from acetylene, then you still got a proton that can be removed by this very strong base. Deprotonate, dump in more ethyl bromide. That gives us an internal alkyne, which I've said we can selectively reduce, stop the reduction at the double bond, and specifically obtain the cis alkene. How do we do that? Somebody say it. H2 with the Lindlark terms. Good. Those are the classic reaction conditions that will stop the reduction of the triple bond at the double bond and will give us cis stereochemistry. That is a stereoselective syn addition. And then we do our cyclopropanation. This is the only new reaction. We've got to expose the alkene to chloroform in the presence, typically it's potassium tertiary butoxide. Remember, we deprotonate the chloroform, it spits out chloride, so we get dichlorocarbene. That's what actually reacts with the alkene. That gives us our final cyclopropane. And that's also a stereoselective reaction that maintains that relative stereochemistry. Okay, so if you thought that the final exam in Organic 1 was the last time you were going to need to know those reactions, I'm sorry to tell you, reactions from Organic 1 are almost certainly going to be important on the final exam in this class. It's just the nature of the subject. It is a cumulative subject. You cannot avoid the reactions that were covered in an earlier course. It's just the way it is. Want to do another question?
You need to know the mechanism or just...
No, but for a synthesis problem, you don't have to write the mechanism out. For a synthesis, when it's kind of phrased like this, prepare this target, from these starting materials, all the carbon atoms need to come from the starting material. It's just overall transformations. If I want you to write a mechanism, and on this test, I'll tell you, there is no mechanism questions on this test. That's going to be really important on the second test. This test is by far weighted on the NMR because we spent so much time on that. It's the multiple choice part's going to be longer on this test than it is on any of the other tests because it's just conducive. Part 1 is actually 100 to 150 points. Part 2 is 50 points. That's going to be more equal on subsequent tests. So no mechanisms. If I want you to write a mechanism, it will say, I will give you the entire reaction. It'll say propose a mechanism, and it usually says use curved arrows to show movement of electron pairs. Be sure to draw structures of all important intermediates. You'll start to see questions like that. Certainly, the next homework that Alicia will grade is, I think, going to be homework number 5. That'll definitely have some synthesis and mechanisms on it, because that's really what we get into for the second class. So I don't ask you to draw curved arrows to show movement of electron pairs. I'm not looking for a mechanism for synthesis. I'm looking exclusively for overall transformations. Here's another one. And it's impossible at this early point in the course to do a synthesis that doesn't include Organic 1 reactions. It gets a little bit easier as we learn more useful chemistry this semester. So that's our target. We want to make it from, this would be benzyl, bromide, and ethylene. Well, you can start to tell where the carbon-carbon bond must have been formed just by comparing the structure of this bigger starting material. Well, it has the benzene ring, it has 1 carbon. That must be the new carbon-carbon bond. And this is a pattern that you start to recognize when you work enough problems. When you get an alcohol, so we have an alcohol on the carbon adjacent to the carbon atom in the new carbon-carbon bond. That screams epoxide ring removal. when a Grignard reagent, for instance, attacks an oxirane epoxide, it forms a carbon-carbon bond to a less substituted oxirane carbon. In this case, it doesn't matter. When the ring opens, the oxygen ends up one position further away. Okay. So when you see an alcohol where the OH is not directly on the carbon that has got involved in the new bond, but rather one position further away, epoxide ring opening might have been a way to do that. And since we talked about how organometallics react with epoxides, that seems reasonable. So we're back, we're not quite back. We can certainly, let me kind of, now we got to take two different paths. How do we make Grignard reagents? What's the direct precursor of a Grignard reagent? So what organic compound needs to be a reactant in the reaction that produces this as the major product? You make Grignards directly from alkyl halides. It just pops a magnesium atom between the carbon and the halogen atom. The precursor is one of our allowed starting materials. How can we make an epoxide? This goes back to organic 1, but you can make epoxides directly from alkenes if you expose the alkene to a per acid. Typically MCPA is the per acid that we use. So this is actually not that challenging in terms of a retrosynthesis, because it's just a matter of finding a new carbon-carbon bond. All we've got to do is we've got to, let me write it this way, I will make my epoxide. This is one where we're going to have to kind of have a couple of different paths. MCPBA is the classic reagent that turns an alkene into an epoxide. That goes back to chapter 11 in the textbook. Then we take the benzyl bromide, magnesium and ether or THF. That gives us our Grignard reaction, our Grignard reagent. Once we have the Grignard, we can throw in the epoxide. Then we have to work it up in aqueous acid. Remember, Grignard reagent is very strongly basic. The acidic workup needs to be in the second step. There's the CH2. Here's our new carbon-carbon bond. There's the second. That's the product of that reaction. Don't have to write the mechanism, but I'll go ahead and write that because I think it helps you see that that's what we get. CH2 NGBr. What's going to end up happening is the electrons in that carbon-magnesium bond always go